ஹலோ அதெல்லாம் பார்த்துப்பா இல்லை பார்த்துப்பா இன்றைக்கி லீவ் கிடைக்கல. இன்றைக்கி ஒரு இம்பார்ட்டண்ட் ஒர்க்குன்னு பாதியில் வர சொல்லிட்டாங்க. அப்புறம் திரும்ப கிளம்பி வந்துட்டேன். வெள்ளிக்கிழமை லீவு எனக்கு. அதான் வெள்ளிக்கிழமை இல்லை சனிக்கிழமை தான் வருவேன். அது இந்த மார்ச் மாதத்தோட ஃபினான்ஷியல் இயர் முடியுதில்ல, அதனால் நிறைய ஒர்க் இருக்குங்க. அதில் மாற்றிக்கிட்டேன். நான் அவர்கிட்ட பேசுகிறேன். அக்கௌண்ட்டுக்கு முதல்ல வந்துருச்சாங்க. வந்துருச்சுன்னா கூட வந்துட்டு எதாவது பார்த்துக்கணும். ஆறு அப்ராடுன்னு ஒரு வார்த்தை கொடுத்துருக்கோம்.
Hello, am I audible? Hello. Hello. We'll first take some doubts. If either of you have. If not, then we'll move on to some demo codes. Hello. Am I audible? Can one of you just give a hello? So can either of you just reply in the chats if I am audible? So I will go over the demos. Hello? Am I audible? Can just one of you let me know? Okay, thanks. So this is what I have planned for today. So this week's content focused on the idea of unsupervised clustering, and there were two class of algorithms that were discussed. One was this k-means algorithm, and the other type was this agglomerative clustering algorithm. And so basically I wanted to show through a demo how what is the difference between the two of them, and for two different data sets I just wanted to show that. Before we go to the demo, is everyone familiar with the theory of the two algorithms? Or should I cover it briefly? Could not complete it. Okay. So okay. So I'll first cover some basic difference between the two, and so you have the idea of what unsupervised clustering means, right? Okay. So unlike our so unsupervised clustering, as opposed to let's say your supervised classification or some similar algorithm, it will not have any labels on the data. So you have a bunch of just data points, and you just want to group them into whatever clusters they could be naturally belonging to. Since these they are all the data points themselves will not have any labels associated with them. Okay, so let's say we have some data of this form in two features x1 and x2. By themselves there is no particular label for any of these data points. Okay, but let's say you intend to see if they can be grouped into different clusters. So you might ask, why would we be interested in an application of this sort? So do you have any idea why, in what cases we would actually come across such an application? air. Oh, okay. Okay, it's okay. So, one application that I can actually uh, give a brief idea about. Uh, in robotics, I will give you some perspective from that side. So, have you heard of this sensors called LiDAR sensors? Is there on Apple iPads? Yeah, yeah, it is there. So, what does LiDAR stand for? Do you have any? Okay, so a LiDAR is basically it stands for light detection and ranging. Okay, and the idea for this it's a time of flight based sensor, which means let's say this is your uh, some environment, and let's say this is your robot over here, and it has this LiDAR sensor mounted on top of it, and there are some objects in its environment. Maybe it could be a table or a big cupboard over here. Okay, some 3D object, and there could be some more objects around here. So for the robot to perceive what its surrounding looks like, uh, it basically uses this LiDAR sensor, and the sensor will keep on sending beams of light in all directions. For now, I'm assuming a 2D LiDAR over here for illustration purposes. So, uh, as this beam of light hits and it gets back a reflection of it, it measures the time it took for the beam to go to the point and come back, and based on that, it detects how far the object that it encountered in along this direction was basically. Okay, and if we try to see how this beam of lights would look like for the robot in this 2D world. So if the object that, let's say this object, if you just project it onto a 2D plane, I'll put it in white only. I'm just drawing two objects that can be part of the world, and so the sensor would actually go ahead and, so wherever it doesn't hit any obstacle, the beam will basically go up to, I mean it can basically go to infinite, but we'll set those whenever it doesn't get a rebound, we'll set those values at some high value, whatever is the maximum range of its detection capability. So the LiDAR map would look something like that. Okay, so here I am drawing all the lines, but in reality what the sensor itself would look for as the, I mean the data that you will get as the output would be something like that. So only the endpoints. So the sensor would essentially get these points wherever the beam of light hits the objects in its surrounding. And since there is no object on this side, I'll just clear this one. Just to denote the position of the. Okay. So in general, for such an application, you can actually use a clustering algorithm, which will, so for this sensor, for this robot, in its XY plane, these points were just like this. And depending on the number of obstacles around the robot, you could have as many number of these points in its surrounding, and you'd be interested in trying to find out which of them belong to a different object, basically. So if I decide at having this data in hand, so having such a data in hand, if I decide that I'm going to cluster this into two set of data points, my robot can make out that there are two objects in its surrounding, and it can basically decide how it has to plan its path through this space. Okay, so that is one of the applications, you can say, in robotics, where you come across such unsupervised clustering. Now, there is no predetermined label of what this object should have been. It's just some sensor data that the robot got. Is that part making sense? Okay. So now there are two ways in which the robot could have decided to do this clustering. So here it was evident for us that there are very two clear distinctions of two clusters in the data around it. But for the algorithm that is being implemented, in general, it could be any number of clusters. And you'd have any number of data points such like that in the space around it. So for the robot to understand how to process this data, so it can either look at, let's say, it will randomly decide what is the number of obstacles it considers it's around itself. So let's say this was the data. So the robot could choose, like, it needs to classify the entire region around it into two clusters, let's say. So one clear way we can see that it can do this classification would be something like this being one cluster and this being another cluster. Okay. So now, so if the two clusters was a predetermined parameter by the robot, like, it will always do this, but in such a case, the robot would essentially consider this entire region as an obstacle, and it would never consider that it can go through this path from in between the obstacles. And if you want to do some optimal path planning through such an environment, doing this kind of grouping of the entire obstacle region around it, that wouldn't be very efficient, right? So your robot would only consider that this is the only way around this set of points, but in general there might be a much shorter path. So there is a disadvantage to directly saying that the robot should group all the data points into just 2 clusters. So can you think of some way how we can tackle this problem? Did the question is the question making sense, or should I repeat it? Yeah, okay. So the question is basically what can we do since we don't know the number of clusters beforehand. I mean, the environment could be anything. The robot could encounter anything in its environment, and we don't know the number n in which we should cluster our or classify all the data that it is seeing. So how can we determine what to do? So any ideas? Maybe look for distance. Yeah, but in what? From some point. I mean, the data that you are actually having is this is when you say that my robot is located over here, your coordinate frame is actually right over here, and I might have, so I'll just remove this coordinate frame. This is the kind of frame you can actually consider yourself to be part of. So the robot is having some orientation. So from some random point you want to consider the distance. Can you elaborate on what you mean by that? So in our case we essentially got all of these points from our LiDAR sensor, and since we know at what angle the beam was sent when it, so along with the distance we also know at what you can say that what was the heading of the beam that was sent to capture this data. Okay, so that is how you essentially got that this data point belongs is present at this point. So if some random point is what you are saying, we already have it with respect to the origin itself, which is the location of our robot.
Okay. Yes, sir. Yes, sir. I'm inserting the videos. Inserting, sir. Sir, maybe half an hour I will put it.
Any other ideas? Okay. Uh, so before we jump to the solution for this problem, let's first discuss how would we approach the problem if we did know the number of clusters. So if we did decide that the number of clusters that you wanted to classify this entire data into was, let's say, n equal to 2, let's discuss how you would go about solving that. So which point should belong to which cluster? So if there is if you are decided that n is supposed to be 2, you can say that there is a bunch of points which will belong to class or class 0 and class 1. So that is essentially what you are trying to do when you say, so you are basically classifying this point, this particular point, whether it should be belonging to class 0 or class 1. Okay, so ideally if you do the procedure correctly, you should end up with the answer that all of these points belong to class 0 and all of these belong to class 1. So now the question is, how would we get to this assignment? How would we, we have to program it for the robot to implement it as an algorithm and do this on the fly? Any ideas? Can't we go for multi-class clustering? Yeah, here we have two class, like that is also a multi-class, but we are deciding what should be the algorithm. So how can we how would we algorithmically implement such a thing that given some data, I want to classify or cluster it into two sets of clusters. How would I go about implementing it? Do we need to look for both distance and direction? So in this particular case, what I'm saying is that all of these data points that you have, you already have their let's say your robot is at some location. You would consider that location as the origin, and let's say the direction in which your robot's some particular heading is there, let's say you consider that as the x direction, and perpendicular to that direction you consider the y direction. So in this coordinate frame you already know the coordinates of all these points. So wherever the robot sent the beam and got a like response from that, so all these points you already know their coordinates. Okay, So knowing the coordinates, what would be your next step to basically cluster them into the two classes 0 and 1? Points with y plus belong to class 1, class 0 and other way. Oh, okay. But so you mean to say that that would be your algorithm? Okay, but that might work only for this specific case, right? So let's say a bunch of points were also present over here. Oh, okay, let's for the sake of it make it a bit more difficult to do it with that algorithm. Let's say you also wanted a class 2. What would you do? So in that case your n became 3. Your goal was now to classify all the data points into 3 clusters. Would something similar work in that case also? Would we just be able to say y plus and let's say y plus y minus x plus x minus? Probably not, right? I mean, in this case, if I wanted to classify this entire data into 3 clusters uh, for some choice of clustering, let's say it ended up being this way, this being one cluster, this being another cluster, this being the third cluster, and a simple rule such as let's say put y plus equal to a particular class, that might not necessarily give you a good result, right? I mean, it could also end up being such that all of the points were only present on y plus side, then you would not get any clusters at all. I can see that more cluster means more complex solution. Yes. So what I'm in fact what you actually said is a good way of also considering the like approaching the problem. So when you said y plus being greater than 0, or say y being positive as class 0, what you essentially meant by that is actually something called what you are implying with that is something called decision boundary. So your decision boundary was a line like this. Okay, I mean that is what your solution intuitively meant. But in complex algorithms or complex problems where you want to classify this into many number of data points, a simple line might not suffice. So your decision boundary is not necessarily a line at all. I mean, in let's say you wanted to really classify it into all 4 the clusters, you can't do it. Your decision boundary would probably need to be something like that. So this is one decision boundary and this is another decision boundary, this is another decision boundary. So you could have multiple things that would determine what side of that line basically belongs to the obstacle, right? So you would have multiple complex curves that will determine how you would do the classification. Yeah. So I would probably specify the problem as nonlinear decision boundary. And that is the issue that we are trying to solve. Okay, so there is an algorithm called the k-means algorithm. which tries to handle this specific problem. So I will just briefly tell what the algorithm actually does. So let's say the data was like something like this. Okay. So now, what you essentially try to do with this algorithm is that for this algorithm you will give the input as the number of clusters you want the entire data set to be classified into. Let's say you said you want the entire data to be classified into 3 clusters. Okay. So what this algorithm will do is that around the space, let's say your robot is located over here and that is your coordinate axis. So it will randomly put 3 points in the region around it. Okay. So let's say 1 point was put over here, 1 point was put over here, and let's say another point was put over here. Okay. So these are just completely random points. There is no specific reason. I mean, there's no basis on which they were particularly decided. Okay. Yeah. I mean, for the sake of example, I'm saying 3, but in general that could be any number. So the algorithm takes the input from your side. What is the number of clusters you want the entire data set to be classified into? So this is an input. It's up to you. Is it the value of k? Yeah, that is the value of k. Yeah. So k means, the k of that means it refers to the input that you are giving to the algorithm. Okay. So the way the algorithm proceeds is that it will randomly put whatever the number of input you give, that many number of centroids, it will randomly put in the space around it, and then it will try to check from these centroids what is the distance of each of the points. So whatever number of data points are present in your data, it will try to see their distance from these centroid points. So let's say you did it for this particular point. Similarly, you would do it from this point also. So you are basically checking the distance of all the points. Okay. And what you do is that based on that distance, so your distance is a metric. So in this particular case, what I was showing, you chose the metric to be, let's say, the Euclidean distance. But I mean, in general, that could be any metric of your choice. Okay. So for the problem of in case of this robot application, it makes more sense to choose Euclidean distance. So we are going with Euclidean distance. Okay. So once you have found the distances of all of these points from these centroids, I will probably name them. So when you do this, each of the points in your data set that will be closest to at least one of these clusters. So this particular point is probably closest to this 3 centroid. This particular point is also close to this. In fact, probably this is also close to this. This might also be close to this. But this point might be closest to this.
Content study, video.
So based on that, you can classify all the points which are closest to this 3 point, and I'm going to mark them with orange, and another set of points which are closest to the 1.
I don't want it here. Isn't it come on top of the text?
So basically we have k bags and we fill those bags with nearest points. Yes, exactly. So doing this, we got clusters of this sort. Okay. So, and our next step is actually that so all these points were said to be part of this 2 cluster. So you would take the mean location of all of these and transfer your 2 to that location. And similarly for these, so you would take the mean of all of these yellow points and transfer the 3 point to that location. Since these are also present, I am putting it over here. And similarly for the 1, it looks more or less in the center of it. So calculating means of each bags. Exactly. Yeah. And once you do that, this will be your new location of the 2. This is the new location of the 3. And probably this is the new location of the 1. So we get k new means. Exactly. And you would keep on doing this algorithm until there is no change in the bags. So there is no change in the contents of these bags. So the same number of same data points are part of the same cluster. Till that point you would keep on going, iterating this algorithm. Okay. So that is the idea. Okay.
This makes sense because it is using API to do the avoidance, just like this.
So how can you devise an algorithm which can, instead of choosing fixing this n number, repeat till no longer. Yeah, that is the idea. Yeah. That is the criteria for stopping the k-means.
There is no need to work. We are presenting whatever we are in the best possible way that we are present.
So in this case, you already knew the number of bags into which you wanted to put it, but using this information, whatever we just tried, can you think of a algorithm where we don't need such a input? Okay, I will kind of give a hint. So instead of looking at distances from a specific uh, chosen centroid, you can look at the distances between the points of the dataset itself.
The process where the student is doing, ask them to read this. Okay, so the way we want to tell the story is slightly different, not the way in which we are putting it here. The reason is the story we want to tell is we tell it this way. Okay. Switch off and switch on. Stop. Stop. See the story and the problem is reading examples of but we want to show our results usage. How we can measure the experience of life. We include one paper's many results that I will give tomorrow. Okay, this one. But the other part, the rest of the part which we are doing, I'd like that to be more media oriented. Okay, so tomorrow you and I have to sit together about it to finalize the presentation.
Yeah, that's exactly the idea. We check the distances of all the points from all the points basically. So the way we would approach this problem is that let's say you sort, but how will it solve our problem? Okay, yeah, we will come to that. So if you do find the distances of all the points from each other, you can kind of even sort this entire thing,
We will not be in the quotation. We can also not find it.
and there will be, let's say, two particular points in this entire data set which will be the closest. I mean, their distances from each other will be the smallest. Okay, let's say those are these two data set points. Okay, so what you would do is, once you have figured out which are those 2 points, you would go ahead and merge them into one single point. Okay, and then you do the same process basically, and you check the distance of which was the second closest pair.
We have to see how to get it into within the time.
Oh, missed the point. Okay. So the first step that you did was you found the distances of interpoint distances between all the pairs, and you found the 2 points which are the closest to each other from this entire data set. And what you did was you merged them both. I ended up removing more points. But the points which were closest to each other, you merged them together and you made it 1 point. And you do this replace with their median. Yeah, basically. So you merge those 2 points, replace that with the center of those points, and you keep on doing this process, let's say. And what you would end up with is ultimately all these points are going to be grouped more or less together.
But at the same time, it can real time be operated upon. So it's a simulator.
How do we think that way?
Which we are looking forward to. So how can we vehicles operate with each other? The future also should consider. So we should look at
No, I mean, this is not my algorithm.
And then we also want to bring AUV appointment, AUV appointment. These are future.
I mean, this is the standard algorithm that people implement.
That is how we should.
So that is the idea of this agglomerative cluster.
The flow picture. This is not telling the story. The slides are good, but they are not telling the story, the right story. The right story to tell is that the bigger section and three disciplines. Okay. The three disciplines.
So if you when to stop? Yeah. So I'll come to that. So in the previous case, our measure was based on the number which we decided, right? So this 3 number was given by us as to what should be the number of clusters. In this case, our entire procedure is based on the interpoint distances. So our stopping criteria is also kind of based on the same idea. So there is a maximum distance between 2 points beyond which you will not merge them. So if all of these points did get merged to this point and all of these points did get merged to this point, the distance between them is some specific threshold, and you would say that that would be the input for your algorithm. You would say that beyond this distance, if there is ever such a case, I would not merge them together and I would keep them as a separate cluster. Yeah, that is the parameter of our choice. It's not a hyperparameter because there is no sort of training going on in this process. So you are doing it on the fly. There is no pre-training and all sorts of sorts. Yeah. So that is the parameter of your, so that you will end up giving, that what will be the maximum distance up to which you can decide to merge the clusters. Okay. So that is the whole idea of agglomerative clustering, and there is a way of representing this. It's called a dendrogram. So what we do here is that I'm putting all of these points that I had. Okay. And I'm putting them on a single, as the, let's say, sample index. So each of the points from our data we are putting it on the same axis, but we know the distances and positions of all of them. So what we do here is that whenever you decide to merge any 2 points, you draw some line like that, and so in fact I should correct myself here. We are not actually putting them on the same line. You actually have something like the distance metric. Okay. So this distance metric is what you would have on the y-axis, and on the x-axis or along this horizontal side you are putting the sample indices. And what you are doing is, whenever you decide to, based on this distance metric, whenever you decided to merge 2 data points, so you would draw something like that as a link between them, and let's say whatever ended up being as the new new point from that got merged with something else, then you can draw something like that, and you would keep on repeating the process. So I won't draw the entire thing, but eventually there might come a point where you would have merged a lot of points, and you would have four sources, sort of. So at a particular distance level, I should have. So below this there is a lot of merging which I am not showing. Okay, below this point. But at a particular distance, which was your threshold distance, so there will be a particular threshold distance where you would have 4 different clusters, and you would say that I would stop at this point, and by this point you would have merged all the clusters belonging to a particular set, and all of the points belonging to another cluster would have come to this branch. Same for this branch and same for this one. Okay, so that is another way of representing it, and we'll see this plot also in the demo. So basically that is the entire idea of these two algorithms, k-means and agglomerative clustering, which are the two unsupervised clustering algorithms. Okay. It's not charging.
So what I want to basically show here is, rather than describe too much theory, I want to show that hey, we can simulate leading motions of ships as we observe in the field. We can show some.
So any doubts at this point?
So that is what I call. So this is coming to this kind of diagrams. View of want this and this to do in a similar manner.
Okay, then we'll move to the code.
Then you also include a couple of this fellow's experiments, Krishna's experiment, the maneuvering in waves. And we'll talk about it, show that video, and put one or two plots. Not to ask this fellow to create just like to give you the maneuvering waves. To show that we also are looking at position and maneuvering patterns, so on and so forth. And then you ask that fellow to do quantum system application. Okay. Quantum system application. And ask you can put them
Is my screen visible? Okay. So in this case, I have kind of generated a random data which was actually generated from 4 center points. So you might not exactly be able to put them where those points are, but in reality there were 4 clusters that were used to generate this data. And then you also have a parameter which was deciding what is the standard deviation around those points. Okay, so yeah, I covered the two types of unsupervised clustering algorithms, and the choice, as I actually covered that part also. So the choice is basically depending on your application. So if if for some reason you have a reason to believe that the number of classes in the data are a specific number, you can go with the k-means clustering algorithm. And if you have no idea of, or no prior idea of how many classes you can cluster the data points into, then you can go with the agglomerative clustering. Okay. So hopefully with the demo, I think some more clarity about the methods can be got. So in this specific case, we have some. So in case of unsupervised clustering, you will end up having data of this sort. So as there is no particular label on any of the data points, so in general you wouldn't be knowing what data point is supposed to belong to what cluster at all. So in this case, I purposely put the cluster standard deviation parameter as a bit high, because then from every cluster center there is a lot of spread of the points that belonging to that cluster. In fact, if I do keep this low, you would have a very good way of separating the clusters out. But in most practical applications, you won't have. I mean, you don't necessarily have a very good split of the visual separation of the data. So we are making the task a bit more difficult for the algorithm itself, and there is a lot more spread around the center point for the data. Okay, and this is just to visualize the thing. So one thing that I didn't actually cover during the when I was explaining the theory. So depending on the initial choice, when you are applying k-means clustering, depending on your initial random choice of the cluster centers, the clustering that you will end up with might differ a lot. Okay, so is that part making sense? Yeah, I mean, maybe I will go back to the tab and show. Yeah, so that doesn't necessarily happen. I mean, that is one of the disadvantages of using k-means also. So we will probably see that. So let's say this was your data set, okay? And as you can see now, visually probably this data point is kind of ambiguous which cluster it should belong to. And let's say you have, by your algorithm, you decided to choose the cape to be 2 for your clustering, okay? So there, in that case, let's say the first 2 random centroids that you end up choosing, they end up being at, let's say, this point and this point, okay? In this case, as you do the iteration of the entire algorithm, you might have it such that these points belong to end up in this cluster and these points end up in this cluster, okay? So that happened because of your choice of centroids being this way, okay? So if that was not the case and you ended up initially choosing the first centroid, let's say it ended up right here and the second centroid ended up here, in that case, based on the distances, you might end up having this as one centroid and this as one cluster. So this particular data point, it was not it's not guaranteed to belong to along with these points or this point, depending on where you ended up choosing your initial clusters, centroids. Okay, is that part making sense? Can't we take average of all such clusters? Exactly. So not exactly average. So I mean, you would have some points belonging to. So if one clustering ended up giving you this as the set and the other clustering gave you. So if this was the clustering in one of the sets, and in another iteration you ended up with this kind of clustering. So this, let's say you even if you did repeat your process for 10 times, so there has to be a way for you to basically judge which type of clustering is better. So are you getting that? So we can't take average of the sets. So in one case the set was this thing and the other thing, and in other case the set was this thing and this thing. So there needs to be a way for us to basically decide which clustering is actually more better than the other type. Okay, so can you try to think what would be a way based on which you would decide which type of clustering is better in general? So in fact we can go to the, so a particular point belonging to a particular cluster, what metric can you decide so that you would consider that as more favorable. Any ideas? Okay, I will give you a hint. So think of it in terms of uh, the variance.
You can. Hello?
Hello?
Yeah. Can you ask the question again?
Yeah, so uh, when we are doing the clustering, we want to know, uh, we want to basically decide which type of clustering is uh, going to be better than the other. So in this particular case, let's say these are the red are your data points, and in one
O-
case you ended up with clusters like this. Okay, this is case one. Okay,
Okay.
where this particular data point ended up with along with all of these. But there is another
Okay.
possible clustering scenario where this happened, and this is, let's say, case 2.
Okay.
So you want some way of quantifying, basically, how would you decide which clustering is more favorable. So in some sort of numerical quantification you want. So can you
Yeah.
think of a metric?
I'm not sure, but as you said before, we have to take some reference line and get variance from that.
Can you repeat what you said?
Yeah. As you said before, like we should use variance. If we have some reference line from that.
Actually, I mean, so this is actually the different type of algorithm. So uh, this all this red has been drawn in red. That is actually a different type of algorithm, and uh, this what we are discussing right now is something more general. I mean, it is independent of the algorithm that you are trying to choose.
Okay.
So maybe I will try to give some notations. Uh, let's say x I denotes some data point that you have. So x1, x2, like that till some x m. So you have m data points in your complete data set, which in this case could be all of these red points. Okay, and what you have is, let's say you have one way of classifying it, which you say some xi belonging to so I here denotes the indicator variable. Okay, indicator function rather. So if I take any data point in my uh, any of these data points, and if it belongs to, let's say, a particular class C1, if I want to get its index out, I would use this function. So this function will result out true if it belongs to class C1, and it will return out false if it does not belong to class C1. Okay, so this is just a notation. Is that notation
So
part making sense?
yeah, so you are asking how can we define that indicator function?
No, no. I'm just saying that for now, just see this notation, and
Okay.
I want you to use this notation to determine a sort of a mathematical idea that can be applied, so that uh, so basically you can quantify which clustering set. So if I say I of x1 belonging to C1, I will similarly have I of xi belonging to C2. Okay, in case I had two clusters. Okay, so the union of all both of these is going to give me all the data points in my data, right?
Yeah.
If I have decided to classify all the data into just two clusters, the union of this ended up giving me the entire data set. Okay, so I want to decide on a metric, which I mean I just wanted to introduce this notation. That's why I've done this. So this indicator function has already happened. So the process of clustering has already happened. You want to decide whether this process that has happened is good or bad based on a metric. Okay.
Yeah, got it.
So that metric is what I want you to think about.
What output will the indicator function give?
So if if I pass, so if I throw in any of these data points in this indicator function, it will return out true if that data point belongs to class C1, and it will return out false if it doesn't belong to class C1. So this notation is for class C1. This notation, the same thing for class C2. So this will return out true if the sent in data point belonged to class C2, and if it did not belong to class C2, it will return out false. Okay.
Yeah.
So based on variance, you essentially want to decide what would be a better set classification that should have happened.
So basically, like you told, we have two centroids, right? So if you are taking variance from that, and I'm not sure how we can define the reference line if the variance of xi is from the centroid is less than some certain value.
Okay, so you want to threshold on the
Line.
you want to threshold on the variance basically.
If the xi is above that line,
I mean, there is no
that should
specific
be.
line here. Okay.
Yeah. There is no specific line because that line can be anything. I'm not sure how can we define the line.
Okay, so the idea here is that what you would do is you would look at the inter cluster variance. So let's say in one clustering, do you have two variants? No, actually I will come to the solution. Okay. So let's say one of the clustering ended up being this and this. Okay. So what you do is you check the distances between take the distances, compute the all inter intercluster node distances basically. So you would have d1, d2, so all the pairs. Okay, we need minimal intercluster variance. Exactly. So that is the idea. Minimal intercluster variance. So in one case, let's say you ended up having W1 as the variance, and with this you add W2 as the variance. You would sum them up. So you would sum W1 plus W2. So this was for class or set case 1. Okay, which was, let's say, this case. And imagine another case where this was the clustering. Maybe I will put it in different colors. This blue way of clustering was the clustering that happened in the other case, and you ended up having W1 dash and W2 dash as the intercluster variances for that case. So you are basically looking at the sum of these. So you would look at the sum of all the intercluster variances, and in whichever case the number is ending up minimum, that type of clustering result is what you would consider more favorable. And you will see that the k-means algorithm was actually is a result of this specific minimization function being utilized. But till when we need to check for minimal? So yeah, so that can be based on your decision. So you would say that I will run the algorithm for, let's say, 10 iterations, and I will take 10 times all of these random centroids and then their interclusters variances. I will do that 10 times, and in whichever case that ended up being the minimal, I will choose that as the ideal clustering. So that is up to you. So along with the number of clusters that you are deciding, this is also an input from your side. Till what number of iterations you want to keep on trying this random centroid. It's a parameter, exactly. That's the idea. Okay. Any doubts? How to think like this? I mean, this is just a standard algorithm. I mean, as you get more and more, as you come across more and more such algorithms, you might get some more ideas how to decide on better algorithms. So I will just are these like standard patterns for ML? Yeah, I mean, so all of ML algorithms that you can look at, they are primarily classified as supervised, unsupervised, and reinforcement learning if you want to classify it as its own separate class. So most of these supervised clustering, supervised algorithms, they will have some sort of a loss function inbuilt into it, and you will basically check your function, whatever it is resulting in, that and the that supervised value, which means the ideal output that you want, you will take the distance between them and consider a loss metric based on that distance in some sort. So it need not necessarily be a Euclidean distance, it can be anything. So in logistic regression, you must have seen the softmax function. So that can also be a loss in terms of which you can measure your loss. So different models will present their output, and you want to essentially minimize the loss. That is the fundamental philosophy of all the supervised algorithms. In case of unsupervised, you don't have a specific way, or you don't have an ideal output, but you can minimize this distance sort of metric. That is the idea. In fact, all of ML can be somehow said to be that it's a optimization problem. You will always optimize something. So we will go back to the code.
Hello.
Hmm.
Yeah. So I have one doubt.
Yeah.
So you told you will use intercluster variance
Hmm.
for the minimum intercluster variance for quantifying which to which cluster it belongs better, right?
Hmm.
But if you're calculating the sum, how can you define like uh, which cluster it belongs to? You will get a numerical value, right?
No,
The
no.
variance, let's
So
say.
this is actually, so once you have done the clustering process, you are
Okay.
basically trying to judge whether that clustering process resulted in a good output or a bad output.
Okay.
You are
Okay.
trying to quantify. You are trying to put a number on how good it was.
Or it's not for defining which cluster it belongs to.
No. It is not for defining which it belongs to. For that, you
Uh,
would use one of the algorithms. Let's say k-means or this agglomerative. You would first
yeah. Yeah. Yeah.
implement those algorithms, and then you would say
Okay. Okay. This is just for quantifying the
yes.
cluster.
Yeah.
Okay. Okay.
Yeah. Okay. So, is my screen with the code visible? Okay. So, as we saw, like, let's say this was our data, and yeah, so that parameter that we just talked about. So, how many of outputs we need to consider before we, how many clusterings we need to consider before we can say we have found a best, I mean, to look at the best of from the different types of clusterings. That parameter we have set it to 10 in this specific case. So in sklearn you directly have this k-means function, but whatever we discussed today is what is going on behind it. Okay. So the way you implement it is this thing, and as we saw, it needs two inputs: the number of clusters and the number of iterations for which you have to check. Okay, and that is all. So the return, so output of this function is essentially going to be the centroids of your n clusters. So basically, if you have four clusters you want to classify, your output will be 4 centroids, and the result would look something like this. Okay. So if you did not know, let's say, to put 4 clusters, and you said you judge that there should be only 3 clusters, in that case you would end up getting a different mapping. So in clustering, that is the thing, that there is no predefined best output for the entire process. It's up to you. It's your choice basically in such a scenario. Okay. So we'll look at the agglomerative cluster example also. So this particular thing I'm trying to show it on a like a commonly used data set in like a toy data set in machine learning. So it's called the iris data set. You must have heard of it. So what this data set essentially has is there are 4 features based on which you want to classify which species a particular flower belongs to. So the 4 features are something like the sepal length, petal length, and all of that. Okay, sepal length, sepal width, petal length, petal width, and so on. Okay, so in fact we have loaded the data set. I will try to show some data points from this data set. So if we try to print let's say the first so there are 4 numbers here: 5.1, 3.5, 1.4, and 0.2. They are denoting the 4 features of the first data point. And if we look at the corresponding label of that data point, it's 0, which means it belongs to the class 0. So there are 3 different classes. In fact, I will print the entire Y. So there are a lot of data points which are belonging to 0, and a lot of them belong to class 1, and a lot of them belong to class 2. Okay, so we are kind of considering this as our data set. So for the sake of show demonstrations, since this is a 4-dimensional data set and we can't visualize how it would look like in 4 dimensions, so what we are doing here is we are using a technique called principal component analysis. And in some few next I think the next week or so, you will see what this technique actually does. Very briefly, if I wanted to tell, what this technique is going to do is, in the 4-dimensional space, whatever these each of the data points that you have are, wherever they are located, you would look at, since you have put n components equal to 2, this algorithm, what it will do is it will try to find those 2 directions in which the variance of this data is the maximum. Okay, and it will basically draw 2 lines, you can imagine, in 4-dimensional space, and it will try to project the entire data set along those 2 lines only. Okay, what this ultimately results out is that you would end up getting your entire data set being plotted into 2D space, since you projected all their values along these 2 dimensions. So in reality, this PCA1 and PCA2, they have no physical meaning. So the real data parameters that you started with, the features, they had some physical meaning, like sepal length, petal length. So they are specific, they have some physical meaning to associated with them. But when you have done this principal component analysis, you ended up transforming the entire data into a different space, in which you did end up getting the projection of the entire data set into a lower dimension of space. From 4 to you ended up getting to 2, but these parameters themselves, they have no physical significance. They are just some random directions. It's a dimensionality reduction technique, exactly. Okay. So we kind of implemented that, and ultimately these are actually the 3 classes in which the data set, the 0, 1 and 2 classes that we saw, these are the 3 their names. Setosa, I'm not familiar with the species of flowers, but these are the 3 classes. Okay. And they have been so naturally, if you see, since there is a projection in this PCA space, there is some way you can actually imagine the entire data set being clustered, but you will see what the algorithm that you will apply. Let's say now we are going to choose agglomerative clustering. It will not necessarily give you the same clustering, because when you did dimensionality reduction, you did lose some information. Okay. So, but you will see the algorithm will still do pretty good job. Oh, okay. And run this. Is it advisable to use apply PCA to any data set? It depends. I mean, if you have way too many features, and let's say there's some thousands of features, and you don't want your model to work with such a high dimensional data, then you might decide to apply PCA. But in some cases, it might not necessarily be useful to apply PCA, because there is always a chance that you might lose some information also when you go to a lesser dimensional space. So not always recommended, but depending on your application. Does that answer your question? Okay. So you might say, like, as we saw in the session, the agglomerative clustering, that really did not require any number of clusters as a parameter. So why are we having this as here? But I'll come to the way, the reason why it is showing that over here. So before that, we'll just look at the result of what it did end up showing. So the clustering algorithm ended up classifying the data into these sort of clusters. If you look at these points, they are actually belonging to this particular class. The blue, this data point over here is actually belonging to this class, but the algorithm ended up classifying it belonging to the green class along with this. So, but overall it did a pretty decent job of classifying it. So some information was lost in the process of reducing the dimensions. So this particular example actually shows that since our input data set itself was only 4 dimensions, applying PCA didn't really help that much. Okay. Now coming to the, so this is the dendrogram that I was talking about, and you might see that if you choose, let's say, something in between, close to this value, where this entire cluster of data and this set of data, they are getting combined at this point, and if you choose something just above that, and you cut this entire thing, you'd see that all the data points, sample indices over here, they have kind of combined and given you they have resulted into this particular cluster, and all of these have resulted combined to give you this cluster, and all of these have resulted to give you this at this point. Okay, so when you did choose your distance threshold, let's say somewhere between we might say this might be some 1.7 or something, or 1.8, so something in between 1.8 and 2, if you did choose your distance threshold, you would see that the entire data set can be clustered into three values. So that is actually what this metric is actually doing here. So specifying 3, you ended up so specifying that 3 ended up giving you this the distance basically where the thresholding can happen. In applications where the way we discussed for the robotics application, in that case you would specify the distance itself, and wherever that thresholding happens, you would stop the process, and whichever data points belong to that cluster, you would stop bunch them together. So that is the process that happens. Okay. So that is all I wanted to cover, and in fact I have put some comments over. In fact, I will share this collab notebook. So you can go ahead and then check for different methods. So the basis on which you want to group the points together can be either based on what is the minimum distances between the nodes, or it can be the average distance between the two clusters, or it can be some weighted distances. So different metrics can be used, and the week's lecture actually covers those metrics. So if you want, you can take a look at later by running this notebook. You can see what these different metrics result in, how the dendrograms in those cases look like. Okay. So that method parameter you can just vary and see what comes out. So that is all I actually wanted to cover today. If you have any doubts more, you can ask. We need to execute them in sequential order. No. This method parameter of the function, this linkage matrix, if you wanted to see what different metrics do, how the combination occurs in different metrics, for that this they are listed out. There is no specific order in which you have to test it. It's just for your for your curiosity. No. Copy paste that centroid. Let's say maybe I will show one of them. So instead of average, if I wanted to use this single, or let's say complete, I would go and do something like this, and then run the cell. So this would result in a this results in a different the metric itself is different now. So you looked at the max. In fact, so the complete is actually somewhat related, similar to the maximum distance between the points belonging to different clusters. at till that point. Okay, so if that happens, if you use that as your metric to combine, then you would have a different merging of clusters. Let's say you used something different. So the single is actually the one that we saw in the lecture. You are looking at every data point and looking at their combination. So that results in a different grouping. To get more details of these methods, you can refer to the lectures, the weekly lectures. Okay. So that's all I actually wanted to cover for today. If you have any doubts, you can ask, or we will conclude the session. Any book reference for this topic? Actually, in the week's lecture, sir is actually referring to a particular book. So, methods of statistical inference. I don't remember the exact name, but he has mentioned it, and that is the source for all the content of this week's session. So you can refer to that. Elements of statistical learning. Yeah. The author name is some something like that. It starts with T. I'm not very sure. Yeah. Elements of statistical learning. Yeah. Tip. Share. Okay, so we'll conclude today's session. Okay. You have a doubt?
Yeah, hi sir.
Yeah.
Am I audible?
Yeah, you are audible.
Yeah, I just want. I have one doubt, not related to the today's session,
Okay.
but actually it's like a generic question. Like for example, see for regression problems, we have discussed at the very beginning some linear regression models,
Mm-hmm.
and then after that we had some neural network sessions, and then we talked about some kind of like decision tree based, like bagging, boosting, and all those things.
Mm-hmm.
So suppose, let's say we have a small data set, let's say around 60 or 100 numbers
Mm-hmm.
only. So for those kind of small data sets, what do you think is like and it's a regression problem.
Mm-hmm.
So which kind of model should be more appropriate for these kind of small data set? this thing.
So
What do you have to say?
it actually depends on the type of features that you are working with. So a neural network model, the problem with neural network model applying for such a scenario would be that you wouldn't know whether your model has overfit, because the data is so small that even if you did do some splitting, it wouldn't really help you figuring out whether your model has overfit or not. So neural network might not be a good way, let's say in most likely for a very small data set. You might consider, the depending on your features, you might consider linear regression. That could end up giving you a good model. In fact, there is a variant of linear regression called Bayesian linear regression, which essentially gives you a, so it doesn't only give you the final answer, it will also give you let's say an error bound around that value. So that probably would be the best algorithm that you can apply for such a case where you have very few data points.
Okay, but you mean to say, okay, I have tried actually with this multivariable linear regression.
Mm-hmm.
But the problem what I am facing there with the data set is that, see, linear regression, we ultimately, our hypothesis is that the model is linear in nature.
Yeah.
So, but there is non-linearity present in my data.
Mm-hmm.
So when I'm plotting the error function,
Mm-hmm.
the residual has a very peculiar shape. Basically, it is not coming in random.
Okay.
So that means that there is some pattern in the data which this linear model is unable to capture.
Mm-hmm.
So in that case, then what should I do? Should I go for some kind of boosting method, or should I go for maybe some other basis functions?
Yeah, I
Like,
mean, yeah, those are the two options actually you have. So either you can go with decision tree based classification, but then again, there also the chance of your
overfit.
overfitting can happen, because the data is so few that you wouldn't come to a conclusion whether the model has overfit or not. So
Yes.
even if you do end up fitting perfectly on the entire data set, unless you have some extra data against you which you can verify, the process might not stop.
Yeah, correct.
So decision trees would be one way, and the other way would be, as you said, so whatever your input linear features were, you can take let's say higher order multiples of those. So let's say you have some x1 feature, you can take x1 and x1 square. So x1 square is also another feature for you.
Yeah.
So that polynomial regression methodology, that also you can try out.
Are there models available in this Python library, machine learning libraries, where we can directly use some kind of nonlinear basis functions?
So ideally you would have, you essentially yourself need to create that basis, the matrix.
Okay.
So because for your application there might be some very weird, let's say sine of x might be a good feature.
Yeah.
So there is no predetermined way you can figure that out, right?
Understood. It has to come from the domain.
Yeah, it has to come from the domain knowledge. Yeah.
Okay. Okay, fine. Got it.
Yeah.
Thank you.